Hello, Drew. So I saw your message regarding the this assignment which is due, which was supposed to be due this week. But if you would have noticed, I've changed the due dates for a couple of the assignments, which includes this homework 3, which was the IP 4, week 4 IP, and also the midterm exam. So I've delayed the midterm exam after the break, till after the break, and the assignment has been moved over to the 25th, right? So I wanted to use today's session, maybe part of it, to address, since we have a very small class, and it's just yourself and the other student, Matt. So we can basically move forward after everybody is up to date on the content. Otherwise, it's not going to make a lot of sense, because some of these concepts are going to be used in the future material that we're going to be covering. So if you're not up to date on this one, then there's going to be issues with that. So could you share with me the areas that you had trouble with, so we can address those specifically?
So I guess when I'm looking at design number 1 from homework 3, if it's been pushed back, then I don't want to get ahead, but I don't want to. I like to do the homework assignment before I forget it all.
Sure.
So
sure.
It was just confusing where they're like the examples you had in previous lectures. You showed 2 sources of voltage, like you had a V1 on one side and a V2 on the other side. And
Right.
this looks similar to another homework assignment that we have.
Right.
And I tried to redraw it to say, does it also mean this? Like, it's hard for me to explain what I'm.
Sure. No,
That's why I scanned it and sent it to you. So
yeah, so I'll have a chance to look at it then. But one of the examples that I didn't had a chance to cover last time had similar approach to one of the homework problems. The other one, I felt like I chose that one because I thought it doesn't require the complete solution, because the 2 current sources that were present there, they were essentially given without any values there. So you could, again, the goal is this. So just before we move forward, I just want to give a generalized. We talked about how to assign a reference node, how to assign independent nodes, and then be able to draw the currents, the directions, and so on. But one thing that the current source does for us, it's just basically we don't have to write it in terms of the voltages, because that's a constant value typically. So for example, in that one circuit, we had the current sources given as IS1 and I sub S2. So the goal is to bring them to the left of the equal to sign, because these values are essentially going to be the constants, right? These are going to be the constants. And then what we want to do is, let's say we have 2 equations, 2 unknowns. So we want to, let's say if I represent the 2 voltages, so there will be some coefficient here. And again, the sign could be anything plus minus depending on how our polarities are. And then there will be some coefficient here. And same thing here, we will have these values. Again, this could be a plus or minus, depending on how we draw the arrows on our circuit. Now, whatever that I wrote here is going to be part of your, so if let's say if you're given values in general form without any specific numbers, which is the case here, then you need to bring it to the standard form of simultaneous equations, right? So you bring it to the simultaneous equations, and then you can leave it there, and that should be an acceptable solution. If you, or you can bring it, if you want to go a little bit one step further, you can bring it to the matrix form. But you cannot solve it with too many unknowns. Right now you have two equations, and we have 4 unknowns, so it's impossible to solve this because these two values are given in the general form. But it shouldn't hold you from writing it in this form. So what you will get then is this. Again, if you'd like to write it in the matrix form, then basically whatever these two, the 4 coefficients are, I'm just generalizing it. You will write them like this. You will have the v sub a, v sub b equal to the two current values, I sub s, I sub s1, I sub s2. If those current sources, for example, had some values to it, then these values are going to be replaced by that. But in this case, we don't have them, right? So I have one other example that I will go over, and then of course we can have a discussion about any area that is unclear. But typically, when you want to bring this, if you have, let me just say this: if you brought your solution to this form, you have done like 90% of the work, in my opinion, right? So I think that is one of the major part of this. The rest is just solving for the unknown quantities, which is essentially going to be the VA and VB, if those are the unknown quantities, and then based on those two, then you can obviously solve other unknown quantities. But again, the setting up the equation is, I think, in the most important part of this whole process. So let's take a look at this example here, and hopefully it's going to give you some idea about how to solve the other problem. So let's look at this. Okay, so we're asked to find some values also. This is a 5 ohm resistor. This is a 10 ohm resistor. And this is a 5 ohm resistor. This is 15 ohm resistor. And this source is at 3 amperes. Okay, the current source is at 3 amperes. Now, if we look at all this, again, this node at the bottom here is a very good candidate for reference voltage. So we assign the reference voltage of 0 to this node, and based on that, we will determine what other quantities are. Let's look at what other nodes we have in this circuit. So we have one node here and one node here. So we will call this node V sub A, and the voltage at that node V sub B. Now I have to solve, I'll have to write equations for both of these nodes. Now, if you don't know how to start, the best approach is just to say, let's say on the first one, you could do that. On the first node that you're writing the equations for, you can just simply say the sum of all the currents there is equal to 0, and you can take them as positive. Again, if you take them in the wrong direction, essentially what will happen is that your polarities are going to be opposite. So but the solution would still exist as the correct form. So what I'm saying there is that I will I will say that there are three currents entering this node here. Okay, one current is flowing in the 5 ohm branch, the other one is flowing in the 10 ohm branch, and the third one is flowing in the 15 ohm branch. I'll just call them I sub 1, I sub 2, and I sub 3. So I'll just simply say, I'm not going to use I sub x yet because that is an unknown quantity that you have to solve for. So I'm just going to simply say that I sub 1 plus I sub 2 plus I sub 3, the sum of all of them is equal to 0. Of course, what that means, if we consider all of them as positive, that means one of the signs would be opposite, which is going to negate and give you a 0 for the sum. So, but as we have marked it the way we have labeled it, so we'll just label it like this. And then that is going to hold true in the sense for the part of this equation. And then the rest of, for example, this current we will label as I1. This one we'll call it I sub 2. This is I1, and this is I3. So now, since I3 is tying VB also into this equation, then you cannot change the direction of that current when we are writing an equation for V sub B. So therefore, on the first, that's why I said on the first node, you have some flexibility in terms of how you want to write the direction of the currents. And once you write them, the currents that are going to be connecting other voltages into this equation, then you will hold that same direction from that point on. So let's just write that, and we will say that the first one can be written as, again, we're using Ohm's law. Okay, so what we will do is we'll say that it's V sub A over 5 plus V sub A over 10 plus the difference of the two voltages, which is, again, the direction is going from, again, it's entering this node. So therefore, we can say it's V sub A minus V sub B over 15. Okay, so we write this, and then since we don't have anything else in this equation, we write it equal to 0. Now we want to normalize this equation by combining the like terms, and you can leave the denominator as is, or if you want to get rid of it, then you of course normalize it in that sense. But again, if you prefer to keep it like that, we will do that. So let's say this one we can then combine. We can say it's V sub A over 5 plus V sub A over 10 plus V sub A over 15 minus V sub B over 15 is equal to 0. Okay, so now over here, if I take the V sub A common from here, and I have 1 over 5 plus 1 over 10 plus 1 over 15, that's one part of it, and then I have V sub B multiplied by 1 over 15 equal to 0. Okay, now you can resolve this by dividing these values. So you can say 1 over 5 is 0.2, 1 over 10 is 0.1, and then you can also do the 1 over 15. So you can do that and write some coefficient here. So let's go ahead and do that. So Could you do 1 divided by 15 for me and tell me what is the exact number there? Because the other two are simple. 1 over 5 is 0.2 and 1 over 10 is 0.1. So that is 0.3. And if you could do 1 over 15, we can add that to 0.3.
Yeah, so 1 divided by 15 is 0.067.
Okay, and then you add 0.3 to that number.
Plus 0.3, 0.367.
0.367 is what I have for V sub A. If you like this format, this is perfectly okay with me. And then V sub B is it's going to be 0.067 V sub B equal to 0. So we can call this one our equation number 1 and then use that to resolve the problem. So now when I go to the second node, then, so I already have one direction, 2 directions are given to me. Let me just label this as this current going down, because the I can choose it like that, right? So now from there, what I will do is I'll take the sum of those currents coming at V sub B, and what I will have then, the current is leaving there. So you can write it minus V sub B minus V sub A, again from the node reference node, sorry, from the independent node that you are writing this, you have to write from that direction. So what I'm saying is from this point, I'm saying V sub B minus V sub A divided by 15, but again, it's leaving the current is leaving that node. So therefore, there's a negative sign there. That negative sign is for that. And then this is 15 ohms. The other one is also leaving it. So what I have is minus V sub B over 5. And then the other current is entering. So I have plus 3, and all that should equal to 0. Okay. Now I need to combine the like terms. So I have minus V sub B over 15. And then this minus on the outside of the parentheses is going to be applied to this middle one. And therefore you will have plus V sub A over 15 here, and minus V sub B over 5 plus 3 equals to 0. So now from this point on, I can combine these two, and I will have minus, I'm just combining the first and third term right now. I took minus V sub B common from it, so both the terms that are left are positive. Yes. I've lost my cursor. Just give me a moment. I have to do the screen shutdown. Okay, so then I have plus V sub A over 15 plus 3 is equal to 0. Rearranging it to just the correct order, we have V sub A over 15 minus V sub B 1 over 15 plus 1 over 5 plus 3 equals to 0. Now, if I write this one based on the previous calculation, we have 0.67 V sub A minus, this is 0.2. So we will have 0.267 V sub B. And then remember that we want to bring the constants to the right-hand side. Okay, so I'll shift this constant to the right-hand side and I will have -3 there. And this is going to be my equation number 2. Okay, now what I need to do is I will get the value of one of the unknown quantity. So one way of writing it is, again, if you use your graphing calculator or MATLAB. So I'm saying that because other student mentioned that he was interested in MATLAB, so I just have to write it in that form. But if you prefer to write your expression, solve the expression from these two equations for the unknown quantities, you could do that as well. So here I have 0.367 as the first coefficient, and then we have 0.067. It's a negative number, by the way. This is from equation number 1, these two values. From equation number 2, I have 0.067, and then I have from the second one term, I have 0.26. This is the decimal point, and then I have the two unknown values of V sub A and V sub B, and then I get the two constants. So the first one has a 0, so there's no constant in this in that. But the second one I have -3, and then this can be solved. So now from this expression here, if I consider equation number 1, and I get the value for V sub A, I will get, let's see. So now this is from equation number 1, by the way. Okay, so let me write this from equation 1. Okay, this is from equation 1. So we have 0.367 V sub A. 0.367 V sub A minus 0.067 V sub B is equal to 0. I shift one of the terms to the other side, and I will get 0.367 V sub A equals to 0.067 V sub B, and then I can write it V sub A equal to 0.067 V sub B divided by 0.367, and this is equation number 3. Okay, now what we can do is we can put equation 3 in equation number 2 and solve for the unknown quantity. So equation number 2 is given there, and I can just simply say it's 0.067 times 0.067 So you have to do the multiplication of 0.067 times 0.067, and then we have to divide that by 0.367, and that should give us some value. Okay, could you multiply that 0.067 times 0.067?
Just multiply 0.67 times 0.60,
Yeah.
0.067 to the power of 2.
Yes, squared it.
So it's going to be 0.0045.
And now divide that number by 0.367.
0.367. It's going to be 0.0122.
0.0122, right?
Yep.
Okay, and I have that number, and then here I have 0.267 v sub b equal to -3. So you want to take this number now that you just wrote and subtract the one that you just calculated, and subtract 0.267 from it. So that number minus 0.267 should be a
like 0.255.
minus negative number 0.255.
Yeah, negative. Yeah, I'm sorry, negative 0.255.
0.255 v sub b is equal to -3, and we can actually, do you agree that we can cancel these negative signs since both sides are negative? So we can cancel them, and then we can say v sub b equal to 3 divided by 0.255.
So want me to divide?
Yeah, so 3 divided, yeah, 3 divided by 0.255.
3 divided by 0.255 is 11.76.
Okay.
11.75.
11.75. Okay, so that is my voltage at the point v sub b. 11.75 is my value. Now what I could do is I can plug in this number into equation number 3. So we can just write it here, by the way. So plug v sub b equal to 11.75 in equation number 3, since that is set up to calculate the v sub a anyway. So we have v sub a equals 0.067 multiplied by 11.75 divided by 0.367. So let's find what is the value of v sub a then.
Sorry, I'm trying to write this down and follow along.
Okay, sure.
Yeah.
Sure, no problem. Yeah, take your time.
It seems like we're kind of jumping all over the place and plug,
Yeah.
0.067 times 11.75 equals divided by 0.367. It's going to equal 2.15.
Okay, 2.15. Okay, so that's my voltage for that. Now, just to understand, how we go through this process of simultaneous equations, is that we first, so we have two equations, right? So we have two equations, two unknowns, And what we do at that point is we take one of the equations, and one of the unknown value is expressed in terms of the other unknown. So over here we have v sub a and v sub b are the two unknown values. So I'm writing v sub a in terms of v sub b. So I can do that from any one of the two equations. So I chose to use equation number one from here because we already have these two equations from the nodal analysis that we have found those two equations. So these are my equation number 1 and 2. And then I took equation number, I started with equation number 1 since it has the least number of terms. So I thought it would be a relatively simpler calculation. So I express v sub a in terms of v sub b starting from equation number 1. So what was equation number 1? It was 0.367 v sub a minus 0.067 v sub b equal to 0. Then I wrote v sub a I derived the v sub a from there. But again, it was not the final value. It was just in terms of v sub b, and I assigned an equation number to that because then I can come back to it and find the value once I determine the value of v sub b. So then I take this value, and the equation that I have not touched yet, I will put this into that equation. If I take it, put it in the same equation, is because I've already got this one, so I'm going to get the normal equation. So what I will do, I'll plug it into the other equation, equation number 2 in this case, and then the only unknown in that equation is going to be v sub b, and then I can solve for that. And that's how I got my v sub b. Now, once I have v sub b, I already have this equation set up to find me the value of v sub a in terms of v sub b. So now I have v sub b, I plug in the v sub b into that equation, and that's how I got the second quantity from there. Okay, so that's sort of the process. I mean, it's just simultaneous equations are solved in this way. The other alternates are the matrix solution. So now we have these two values. Let's observe what is our what are we looking for. Okay, so then one of the value that we have to find is v sub x. Now I know that the voltage at this point is 11.75. So the voltage from this point, which is 11.7 v sub b, to the reference volt point, which is 0, is going to be that the voltage across that branch. So in other words, this v sub x is equal to v sub b. The other way of looking at it is that I know that v sub b is across the 5 ohm resistor, which is the voltage here. So this is v sub b because it is directly going to the ground. Sometimes we can get a little bit confused by saying that how can there be a voltage across a current source? But again, there is a voltage across a resistor. That's just commonly used. So I mean that there should be no confusion about that. So once you have the voltage in that branch, then you know that voltage across parallel branches is the same. So the current source is the parallel branch. So we can then say that v sub x is also equal to v sub b, which is equal to 11.75 volts as we have calculated it. Okay, now for I sub x, if we look at I sub x, it is the current that is going through the 5 ohm resistor. So as far as the polarity is concerned, let's say if we mark the polarity as such for this, it's going to be opposite of I sub 1. But if I take this in terms of the I sub x, it is going to be, this point has v sub a voltage here, right? We know what v sub a is. We know this one is 0. So the difference between these two, so we can then say I sub x is equal to v sub a minus 0 divided by 5 ohm. This is the same way we have been expressing it in terms of Ohm's law. And then you can solve for that, which is 2.15 was what we calculated it as, divided by 5. And this is going to be 0.43 amperes. Okay, so that's going to be your solution for I sub x. So sometimes you're going to be asked to find other quantities in the circuit also. So that's generally the process. So let's have a discussion about this problem, since we will not discuss the homework problem specifically, but let's discuss this problem. So are you clear on the process that we followed in terms of the solution of this problem?
I mean, I get about halfway there, and then I don't know what happens. I just I don't understand how, like, all of a sudden we're gonna plug equation 3 into equation 2, and then we're gonna plug, you know, it starts to, it gets all muddy. So I don't.
Okay. So I can see the problem there, that you're having issue with solving the simultaneous equations. But as far as setting up the equations, do you have any trouble with that? Are you able to set up the equations the way?
Well, I mean, I guess, you know, I mean, I'm trying to figure out the node voltage equation first. Like, that's my first step.
Okay.
And it seems like I can't, you know, I can set up a node voltage equation. You know, I1 minus I2 minus I3 or whatever equals 0.
Yes.
But I guess I keep having the same problem with the homework doesn't have arrows, so I just put in arrows where I want them, and then if I put in an arrow, then, you know what I mean? It's
right. Yeah. So like in this example also, there were no arrows, right? So if there are no arrows, what I did was I just directed all the currents entering that first node. Again, we have the luxury of doing that, right? On the first node, you have the flexibility there, right? So you can, so even though it will not be a realistic scenario that, you know, that let's say this is a node, let me just take it out of this system a little bit. And generally, so this one was 5 ohms. This one was,
that makes it easy because you just add everything to equal 0.
Exactly.
Then
if the directions of that specific currents do not add up, it would be a negative number, right?
And out of the circuit, I want to pick out a independent node.
Right. Right.
It seems like what I'm talking about is I don't see an independent node, because there's V1 that's with the two. I guess it's in my question that I emailed you. So I, like in your example, I know which one's the independent node. So I know how to create a node voltage equation, and then just go nuts, keep going and going and going. But and then halfway, I don't know. But you know.
Okay. So in the other question, you said that you were having difficulty with the other question of the homework assignment. Let's see. Let's use that as a general form, and then so again, as far as this is concerned, if you see, so the first thing you want to show is the independent nodes. Independent node is any node at which you do not know the voltage. Okay, so that's the definition of independent node. That's how you identify an.
Oh, I thought it was the independent node was the node that wasn't touching the voltage side or whatever.
No. If you remember our previous, let me just show you one thing here. In our previous lecture,
like I wouldn't choose node 2 because it's technically 2 nodes. You know, I'm gonna pick a node that just has one black dot and it's not, you know.
Okay. So in this, let's look at this one first, and we move to that question. This is the example that we solved last time, right? So if you see this, what is the definition of a node? Definition of a node is if it combines two elements, right, that would be a node.
Okay. I thought a
If
node was in between two resistors or in between two.
a voltage source, a current source, and
Well,
that would be.
no, I know. So I know that that's a node, but I guess more so the node voltage equation, you want to start off with the independent node.
Yes.
So
Yes.
yes, that's a node, but I need to find the independent node, which
Independent node.
is a
this
node
one
not touching a voltage source or whatever.
Right. So this one is a great example. If you look at this circuit here, so we have, over here, again, I'm having. Give me a second again, I apologize. Okay, so over here, we have determined that we have 5 nodes here, right?
Yep.
All of them qualify as combining at least two, two components or two resistors or resistor, voltage source or voltage source and voltage source. Now, if I look at node number 1, I can see what is the voltage there, right? Because node number 5, I've already assigned a 0 voltage to that. So then that by definition cannot be independent node because we know the voltage is 0 there.
Yep.
If I look at node number 1, there's only a voltage source between that node and the reference voltage. So of course, as you said last time also, that the voltage at that node number 1 is going to be 128 volts, right?
Yeah.
So we cannot call node number 1 an independent node because we already know the voltage of that. Same thing can be said about node number 4, where you have 320 volt source tied there. So therefore, with respect to the reference voltage, it is also 320 volts at node number 4. So that cannot be considered as an independent node. So that leaves us only 2 nodes in the middle, which is node number 2 and node number 3, which are independent. So in that sense, then we solve equations for those 2 nodes. Now coming back to I just wanted to show you the case where you have a node, but you know the voltage of
No,
that.
I understand the difference between a node and an independent node.
Okay, great.
Yep.
Great. So now over here, if you look at this, if again, just visually, we can say, okay, these are 2 different nodes, but they're technically not, because if you look at that, let's say a node cannot combine, cannot have a wire between a node. So node cannot be touching a node. Then it is not a node. If it's touching the node, it's the same node essentially. That
So you
makes
don't
sense?
have node VA, like node
VA is a node, but again, you cannot say that this one is VA and this one is VB, right?
Oh yeah, I get that. Yeah.
Yeah. So that
VA is one node encompassing 2 black dots.
2 black, exactly, because there's a wire between them. So if there's a wire between that it means the same electrical point and hence the same voltage there, right? So then we can say that this is the same node, right? So we call it V sub A. And since we do not know the voltage at that point, V sub A is unknown. So therefore we say that this node A is indeed an independent node. So I will call this one A, and I'll call this one B, and I'll call this one C. So C we assign a reference notation to. So therefore that is assigned a 0 value, so that there cannot be independent node. But that leaves me with A and B, and I do not know the voltage of either one of them. Now, if this particular current source was a voltage source, in that case, I could not assign node B as an independent node, because then that voltage would be across between the that point and the reference. So therefore, then you will have uh, issue with that in that sense that it's not going to be independent. So then you will have only one independent node, right? That makes sense.
Yes, I know the difference between a node and an independent node. It
Okay.
makes sense. Yeah, we're saying the same thing.
Okay, sure. So once you have classified all the independent nodes and you have identified them, then all we have to do is on the first node when you're writing the equations, if you don't know where to start, the best approach is going to be to simply just take the sum of all the currents and equate them to zero, like this, right? So that's a
Yep.
good starting point, right? And you have the flexibility to write the currents in any direction that you want, as long as they are consistent across the entire set of equations. Now, over here, I chose this direction to go in the other way, but I could have chosen it to go up also. But if whatever direction I choose here will not have impact on the first equation because it's not part of that first equation. But this I3, the direction that I assigned in the first equation will be considered for the second equation with the same direction also. You cannot choose it to be opposite direction in the second equation. So therefore, any direction of any current that is flowing between the two independent nodes, that current direction you cannot change, but all other once you define it, right, once you identified it, all the other currents you have flexibility of choosing the direction. It will not have impact on the solution of the problem, right? So once you have done this, you have drawn the arrows, you write the equation, then you write the currents in terms of voltages and resistances. So you just apply, of course, the Ohm's law. So I is equal to V over R. So you write it in terms of V over R's, and you get a final equation which is in the most simplistic form. And once you have, because it's easier to solve if you're going to be doing it by hand. So therefore, you take that equation, you derive as. So now, if there were three nodes, I would derive three equations, right? So then you will have three equations, three unknowns in that case. So you'll have three voltages to look for. But in this case, we have, so far with the examples we've been working on, we're only working with two voltages, because if you get to three, it's the same process. It's just that you do the substitution more times. Now, looking at solving the simultaneous equation, which seems like you are having some trouble. So let's look at this. So we started out, I'm just going to go over this problem.
So before you go any further, so if I see a diagram and I see V1 and V2, V1 is a power source and V2 is a power source, correct?
Yes.
So when I know we're not trying to talk about homework, but homework 3, there's no independent node. So I don't know how to formulate a node voltage equation if there's no independent node.
Okay, so you're talking about, let me bring, I'll just, we're not going to go through the solution, but we will discuss that problem.
Yeah,
so let me open.
that's fine. But that was my question to you, and it didn't have to take up or consume, time for other students to, follow the lesson and the lecture. But that was,
Okay. Okay, so it was that other problem. Let me just open that real quick and.
Well, because I don't even think we've talked about the other one yet. So.
Okay, so if you look at the problem that we just solved, let me just share my screen here. Okay, so if you look at the problem that we just solved now, it looks awfully similar to this design problem number 1.
So there's the V1, and that's a power source, and then there's V2, and there's a power source. And there's no node that's not touching a voltage source.
Okay, so this is, by the way, this is, let me just reduce the font here. So let me correct you there. V1 is not a not a voltage source, so it's not a source at all. It's just a voltage across some resistor. Okay. So in order for us to do, this is also a voltage across this branch. In order for my source to qualify as a voltage source, it will have to be something like this independent voltage source. Okay.
Okay,
So
because that's what I was asking. Like, if is V1
Okay,
a power
sure.
source? So because I'm looking at that as a power source, and then I'm looking at V2 as a power source. There's no independent node.
Right. And if that was the case, then there are no independent nodes. You're right.
Okay,
But-
so that's
Yeah.
that's why I was saying, and
Okay.
to you, I was like, can I rewrite it this way? Like, I don't, and then that adds more nodes. That's confusing too.
Right.
So that's where,
yeah.
perhaps I'm just getting lost in the semantics of it, but
Sure. I think that's what it is. Basically, so V1 and V2 are just, because see, every single one of these elements has some voltage across it, right? So we can say this is V3, we can say this is V sub 4, we can say this is V sub 5, right? So it's just voltage across the resistor.
okay.
But in order for us to qualify it as a voltage source, it has to have this shape, or a current source has to have this shape, right? So that's the key there, right?
Okay,
So
you can see where my confusion was.
I can see now. I can see.
So that,
but
and
basically,
then, so
I
that
did
right
not
there,
understand
I'm
the question
roadblocked. I
the
can't even
process.
get past step 1.
Okay, so
if I
in
can't-
this case,
ahead.
if you make it just a general rule for yourself that if I see a symbol of an independent voltage source, there's a difference between independent voltage and independent voltage source. We just call independent voltage source a voltage source, just to avoid the confusion between independent node and the independent voltage. So if you see the symbol, which is a circle with a plus and minus, then that is the voltage, right? A voltage source, and that will apply to anything. But if you see V1, just like it's written here, or V2, those are not voltage sources. It is just simply voltages across those branches.
Okay.
So if you're setting it up, this is going to be your reference. This is going to be your node number 1, and this is going to be your node number 2. Again, this is not a node, as you know. This one is a node, but again, this is also a node. So 2 nodes cannot be connected by a wire. So therefore, we will say that this is node number 2. So this is node number 1, and this is node number 2. And hence, you have 2 points of reference, and you have independence. So some of the currents are given to you in terms of the direction, as far as direction is concerned. Like
I think I got enough to
move forward.
Let's get past step 1 now. Now I got to implement all the other stuff. So
okay, sure, and do let me know if you seem to see a roadblock.
I appreciate you showing all the steps.
Yes,
and not skipping a step, and then I'm like, well, how,
yeah, that way you can go back to it and solve
I write down everything you write down.
Okay, yeah, I really appreciate that. I see
that. So
yeah, it certainly helps, because and when I'm learning something new, I always take good notes, because those notes, because our memory can play tricks on us. Not everybody has photographic memory, so I forget things. Of course, when there's somebody solving it, I can pay attention. If I'm not taking notes, I can pay good attention to that, whatever is written. But then again, I may not be able to retain it.
It's just I don't know. It's easy to follow along to your lecture. It's not easy to implement my notes and your lecture to the homework when, and I've said this before, when the homework doesn't match the assignment.
Okay.
Like,
So in this case, this particular problem, and forget about the labeling. I mean, labeling could be anyway, but this particular problem is exactly the way it looks, like the last problem that we just solved.
no,
The
I agree.
difference-
And that,
Yeah.
and we clarified why I was having a problem. So yeah.
Sure, sure. And now I just would say, just make a comment about this particular problem here. Now, this one is not a very in a very generalized way also, but it is, so the nodes are labeled for you here, but the current sources do not have values assigned to it. But you will still treat them just like constant numbers and bring them to the right hand side of the equation and write your voltages or write your currents in terms of the voltage. So once you move to that, so hopefully that doesn't cause too much.
No, I'm gonna mess this one up too, because it'd be nice if I had a voltage and then I could solve for voltage or whatever, but
Current. Okay.
We'll see.
Okay. Let me just say this. Okay. Let's do this. We'll modify this problem. Okay. Because it doesn't matter, what values we assign. So let me just say this one is 2 amperes. And this one is 5 amperes.
oh, see, I would have messed that up completely.
Yeah. Yeah. Okay. So now you have those values for these two problems. If you are having trouble with using the general form, so now the resistor values are all given to you, right? Resistor values are all given. And essentially the current values I just gave to you, and the rest is just set of two equations that you have to set up based on the two nodes. One point I want to like to make about the second problem is this voltage, whatever you find for VB, that's going to be the voltage here, which will essentially translate to voltage here. So whatever your VB is, that is going to be your output voltage. So that's, once you find that solution, you can just assign that value, just like we did in the previous problem for the one that is solved, where we found this voltage in the second node, and that was assigned to the current source, just like we did previously. Okay, so hopefully this will guide you in the right direction. And again, always, if there are any issues, we can have discussion about it.
Okay, yeah.
All right, so let's go and share. Okay, so I'm not going to go too much deep into the discussion about the next topic, but I'll just generally introduce it. And we have another lecture before the break, so we will finish that topic then. But so that's is one technique that we just found or used, which is the node voltage method. The other method that we're going to be using is going to be mesh current method, which is the second technique, and they're used sort of hand in hand. And sometimes some circuits are better suited for one technique versus the other, or in some you can use either. And we'll see some examples I'll show you where you can kind of identify that one is better suited. So over here I have a voltage source connected to this resistor. And based on this, we will just write a generalized form. So I'll just use this as a reference. Okay. So we have R1, R2, R3. This is the two source voltages. So let's describe this process. The process is called the So the first step here is that we have to define the currents through the meshes. Okay, so now we have two meshes or two loops. In this case, the three is again the larger loop, but again the mesh is the sub part of it, the smaller part. So in the first mesh, you have to identify the currents flowing through them. So normally what I do, and normally what is acceptable convention, is that you take these currents always in the clockwise direction. Okay, that way you have a system. So you always take this current in a clockwise direction and you label these currents. So I have I1 and I2 here. Okay, so these are my two currents that are flowing through these meshes. So this is the first step that you have to define. Okay, the next step is okay, so it's sort of the opposite of what we were doing before. Before we were using KCL at the nodes. Now what we are doing is we are applying KVL, which is the sum of all voltages across that mesh must be equal to 0. Okay, so we apply the KVL, and then each of those voltages are essentially described or expressed in terms of current and resistance by applying the Ohm's law. Just like we did previously, we are expressing the currents in terms of voltage and resistance. Now we are expressing the voltages in terms of current and resistance. So you can kind of see the similarities between the two techniques. So that's the second step. The third step is, again, it will give you a set of simultaneous equations. So and the number of equations So however many meshes you have, that is the number of equations you will describe, right? So if you have, right now in this example, we have two meshes. If you had three meshes, then let's say if there was some resistance on the top, then you will have the third mesh also. So that's sort of the process. So in this case, we only will have two meshes. So you will write it like that. Okay. Okay, and then once you have developed that, then you solve for the unknown quantities. Okay, so now I need to develop the expressions or the equations for this circuit that we have. But more importantly, I need to get my cursor back. I apologize. Okay, so now based on this circuit, I will write my first equation. So if you look at this, what we have is on mesh number 1, we can write the equation for mesh number 1 by the direction of the current. And since we have identified the polarities there, we will use those polarities. So the VS1 is coming across as a negative number, right? So we have minus V sub S1 plus, I will call this the voltage. Let's call it V1. So let me just label these in terms of voltages. This is V1. This is V2. Based on the subscript of the resistor, I am assigning these voltages. So there's a source voltage and then there's a voltage. So there are 3 voltages across 3 resistors, and I'm just going to write those. And then the third one is plus V2 is equal to 0. So this is the first step. Was I identified the direction of the current. The second step is I wrote the KVL, and now the next part of the second step is to express these voltages in terms of resistance and currents. So I1 is the current there. So for the first one, it's just a voltage source, so I cannot express this any other way. It's going to be a constant value, so I will write it minus VS1 as is. The voltage V1 can be expressed as V is equal to IR. So it's going to be I1 R1. The V2 is going to be expressed. So basically in the R2, there are 2 currents that are going across. So one is going clockwise, the other one is going counterclockwise. So of course they are going in opposite directions. So the difference of the 2 currents is going to be what the current is that is flowing through the R2, effectively whatever that current is. So then we can say that it is I1 minus I2, R2 is equal to 0. Okay, so this is what going to be my, and then you can combine the like terms. So this value is normally going to be a constant value. So therefore, I want to bring this constant to the other side. Okay, so what I will have then left is I1 R1 plus R2 minus I2 R2 is equal to, then the sign becomes positive on the other side, this. So then this is the acceptable equation form. And then at this point, I can just sort of, for reference, assign some equation number to that. Okay, so it's going to be equation number 1. Same process is just that right now we're working off of KVL. Okay, the second mesh has R2 and R3 and VS2. VS2 is again positive in this sense because the direction of the current is counterclockwise, is entering the positive pole of the voltage source first. So therefore, this is going to be expressed in that way. Now, one thing to notice here, to correctly write these equations, when you are considering R2, you will, from mesh number 2, you will have to write the polarity of this. Yeah, this is getting very annoying. My screen is stuck again. Okay, so when you are for mesh number 1, you take the positive sign on the top there in the direction of the current. When you're doing mesh number 2, the polarity is going to be considered like this for this element. So that is just a habit that you have to develop when using this process. Okay, because it's a we write these mesh equations like that. Okay, so now for mesh number 2, what I have is it's I2 minus I1 now. Okay, so we're taking that and we're writing R sub 2 there. Then I have I2 R3 plus VS2 equal to 0. So then that's what I have here. So this R2 will be the difference of I2 minus I1. R3 is going to be just simply it's a positive voltage because we're going to enter the resistor on the positive terminal, and the way this voltage source is given, the clockwise current is going to enter the positive terminal of the battery first, so VS2 will be considered as a positive voltage. So then you have this form. Now let's simplify it further to combine the like terms. So I have I2 R2 minus I1 R2 plus I2 R3 plus V sub S2 is equal to 0. Combining, so let's say I have minus I1 R1, I1 R2 plus, I combine these two terms. So I have I2 R2 plus R3 plus VS2. Now we need to bring it to the general form, which is the constant must be on the other side. So now what I have is I1 R2 plus I2 R2 plus R3 is equal to minus V sub S2. So the constant is brought to the right hand side of the equation, and hence I have my equation in the general form. So at this point, you should be able to proceed further by solving this problem, or you can also write it in the general like in the matrix form. So I'll just write it here so that I have a view of both these equations. So the matrix form has a coefficient matrix, the variable matrix equal to the constant matrix. Okay, so this will include the constants. This will include the variables, and this will include the coefficients. Okay, so for I1, again, I have R1 plus R2. Then I have minus R2, minus R2, R2 plus R3. This one is I1, and this one is I2. This is, again, this is going to be generally a constant value, which is going to be the value of the voltage source, and VS2. So now from this, you can solve it, through calculator or MATLAB that way. But if you choose to use the other technique, then you can essentially, from one of these equations. So let's say if I take equation number 1, and so that I have a view of this equation, I'll just solve it in this blank area here. So let's say if I want to find the value of I1, so I will modify this equation like this. So this is from equation 1. Again, we're talking about the general form here. So I1, R1 plus R2 is equal to, again, the term that goes to the other side will become positive from a negative. Okay, so now you have I1 written in terms of I2, because this value VS1 is going to be known. The R1, R2 are also going to be known. So the only unknown that you will have will be I sub 2. And you take this value and plug it into equation number 2, and then you can solve for the unknown value in terms of, so the I2 can be calculated. And once you find I2 from equation number 2, you come back to this equation, and you can actually call this equation number 3. So you solve I2 from equation number 2 by plugging in this value of I1. So you just replace I1 here by this value and solve for I2. And whatever the value of I2 is, you bring it here, you come back here after you get it, and you will solve for I1. So same process that we used in the node voltage analysis, we use here. The only difference is that the quantities have interchanged between the voltages and currents, and the way we set up equation by observation of the circuit is slightly different. So what I will do for now is I'll stop it here, and we will work on some examples in the next lecture on Tuesday. So I'll show you, 3 or 4 different examples since we have set up this discussion, and I'll show you a problem where you can apply either the node voltage or mesh current method, and which one would be more beneficial in terms of the efficient way in terms of less time consuming method. So you'll have to look at that also. So far we've been only focusing on one idea so far. Okay, are there any questions about the mesh current technique as far as setting up the circuit and finding what the setting up the equations from the circuit?
No.
Okay, I think once
really.
you solve some additional examples, right now it's just introduction of the topic, so obviously there'll be some more clarity would be needed. So once you see some examples, hopefully that will make more sense. So if there aren't any questions, I'm gonna stop the session here, and on next Tuesday we'll see some more examples and hopefully get a better understanding of these topics.
Okay, sounds good.
Okay, thank you so much.